again, my friends. I'll go once more to the cellar that is Leopard Street. This one is, well, partly user requests. I'm going to be having another look at a bit of software. I've been fitting servos for points. I've been setting points up. A few episodes ago, I had a look at the software that drives the board controllers, and I said I would come back to that to look at the software that drives the actual servos. So in this one, buckle up, we're digging into code libraries. This isn't a train running video. If you want to watch trains running, this one's probably not for you. We'll be back to that in the next video. To the desk, this is Leopard Street with a coding video. God help us. Yeah, welcome to the mess that is the desk at Leopard Street. So, before we start, we need to have a little bit of a history lesson and look at a piece of hardware. This is a PCA 9685. Specifically, that's the black thing in the middle with the spider legs. These are modules. They're based on a design by Adafruit, and they're easily and fairly cheaply available. What you do, you put power in here, so 5 volts one side, ground the other. That is your power supply circuit. That connects to these red pins and these black pins down here. The yellow pins are signals. If you go back to a video I did a while ago on how servos actually work, what you do is you put a pulse width modulated signal through here at 50 Hertz. The servo picks that up and it says, I need to do the following. You can daisy chain these boards. These use the I2C interface, integrated circuit, I believe it stands for. So over here you've got ways you can set the address. I've not yet used more than one of these on a board, so I've not had to do that yet. Here are some input pins. What I usually do is take those off because they're the same at both ends. So I take these off because I'm not using that connector, which is the DuPont style, and I solder a JST connector on this side. I take the pins off so I don't have bare pins. And that's the control board. I do make one little modification. Get this. I don't know how well focused this is going to be. There is a resistor here. I remove it. What this does, if I can just grab a little bit of a card. Let's grab one of my little pieces of note card here. These boards, as designed, could be a pen here somewhere as well. Let's see if this one works. Woo! These boards, as designed, you have a line which is known as OE with a bar because it is active low, and that comes into your little chip here. And to keep it low, on here there is a resistor. This is on the board. It's 10k resistor, and it goes down to ground, and it goes into the chip. And that is designed so that if you don't connect that pin, because you don't have to, the board will work quite happily if you don't connect the AOE, which is this one here, second from top. If you don't connect it, on here you've got a whole load of outputs, 16 of them, and they're all active straight away. Brilliant. Now you can have your microcontroller over here say, I'm going to set that to a high level of logic, switches all the outputs off. But in the time between you switching this thing on and your microcontroller booting and saying, make that pin high, these outputs are live. And if you've got this connected to point work, this means the servos may all go down to their 0 point, which you don't want. That can damage things. So what I do is I get rid of that. And then on my circuit board, I have over here a pull up to plus 5 volts. So when it's not connected to anything, it's off. And then the servo, the microcontroller can set it to ground to turn everything on when it's ready. That's the board. Now I wrote some custom software for this. Now why would you do that? Why wouldn't you just use a downloaded library? Well, this is where the history lesson comes in, because this is the point controller from originally from Dingleberry by Engage Layout. This was before it went into its final guise, which has an Arduino Nano doing this. And this, turn it around the right way, this board I got hold of in, I think, 2080, and it's a Raspberry Pi 2040. This is the first generation chip, the microcontroller from the Raspberry Pi Foundation. And it is wonderful. But when it came out, software support for it was quite limited. The Arduino IDE couldn't talk to it initially. It can now, and it can talk to it quite nicely. There are still some bits you can't do with that. So I ended up with a Raspberry Pi 400, which is one of their little computers. It's a magenta and cream coloured thing because it looks like a raspberry with cream on top. And yeah, go figure. And I had to program this thing. Now, I wanted to control one of these boards. As I say, there was no library to do that. So we're going to have a look at how I did that in a bit. But this is a powerful little chip. It doesn't have Wi-Fi. The new ones do. There's I think Raspberry Pi 2 or something. It's got Wi-Fi on board. I gave it a reset button because it doesn't have one. And this little chip over here is an EEPROM. This is a 1K memory chip because there's no memory on these things. And this, the dust off it, it's been sat in a drawer for several years. This is a touchpad. You touch this here to do different things. As you can see, it's set up to work a little bit like a game controller. It's on not very flexible wires. Now, I set some code up so that I could configure the points, and different buttons on this did different things. I think I was tapping these to make the servo move a degree each time. One of the buttons at the top, I forget which one does what. One of them told it, save the settings. Saved it in there. So, unlike where you've seen me faffing around recently, changing code and re-uploading code to the microcontroller, this did it all in one go. I didn't bring this forward into the new ones for Leopard Street because I've now got Wi-Fi. This was set up to talk over the CMRI interface. So basically there was a serial bus connected to this to a PC, and it would send commands to this to move the points, but that was all it could do. So configuration came via this. So I had to write a library for that. Stop my PC going to sleep. Yeah, I had to write a library. So I thought I'd write my own. And it worked. It wasn't perfect. It had a few bugs in it. There was a divide by zero in there. So if you told it to go to position 0, the whole thing just crashed. I fixed that since. I then rewrote that before Dingleberry was finished. I rewrote it to work with an Arduino Nano because I was using those for everything else. So it just made sense. And that's the version of the library we're going to look at today. That's where it came from. This is why I had to come up with my own. There's other ways you can use the existing libraries to do everything I'm trying to do. If you want to move Servo slowly, you've got a little bit of work to do yourself. I didn't want to do that. So without further ado, let's get into how all this actually works. I'll power up the computer. Right, so where do we start with this? Well, what I need to do, first off, is we're going to have a look at this. This is the PCA 9685 datasheet. Because if you're going to write a software library for a piece of hardware, the first thing you need to do is see, how does this piece of hardware work? What do I need to do to make this work? So this is where I started. It's quite straightforward. It's a scary datasheet, 52 pages, but the information you need is fairly early on. So as it says here, I to C bus controlled 16 channel LED controller. Optimized for red, green, blue, amber color backlighting applications. Okay, well, we're not using it for that. We're using it to drive servos. Yeah. And the reason we're doing that is because it can set itself up correctly to provide a suitable source current at 5 volts, which is what we need. We only need low current. So there we are. So the we can do milliamps on that. We can do this here. We can give it the supply. Now this is useful. It works between 2.3 volt and 5.5 volt. Outputs a 5.5 volt tolerant. Now that's useful because what that means is if you're driving this thing at 3.3 volts, say through an ESP32, or the Raspberry Pi 2040, which is also 3.3 volt, you can still hook up 5 volt to it, and that matters. So there we go. So that's what we've dealt with that. It comes down here, staggered on and off times. Now that is also useful. We'll come to why. 4096 steps, so it's 12-bit pulse width modulation. That's useful. Basically, the way the servos, if you go back to my original servo video, you will see you control them with a pulse width modulation waveform. And the higher resolution you can do that, the more accuracy you've got. So there we go. And we'll come on to what servos need again when we start looking at the actual code. It's got an input, so it'll take an external clock, but it's also got an internal clock, which is fine. We're going to be using a 50 Hertz output, so this can go an awful lot faster than we're supporting. So here we have the bit on the active low output enable, which we've set up with that. There are also the ability in software to turn everything on and turn everything off. Don't really use that. Then we come here. So 16 LED drivers. In this case, it's 16 signal drivers. So you can tell them to be on, off, or you can program the waveform. Now that's what we're going to be doing, because that's how we're going to drive servos. As you saw, this board's set up to drive servos. This is a very, very capable board for doing that. 6 hardware address pins, so you can have 62 of these on the same integrated circuit bus. Like I say, I've never used more than one. The software I've got will, in theory, do it. I've never tried. I will be soon. And there's the rest of the inputs on that, so we don't need to worry too much about that. Now, this thing works. If we scroll down here, there's your lovely little block diagram. So there's your bus inputs, the address that controls this. This is set up to show only a single LED, but it's relatively complicated internally. You don't need to know about that. There's the pin connections. You don't need to know about that because it's on a little breakout board. It's nice to know. This is an example of one of these boards where you might think, I could get the chip. I could get the chip and I could just make my own little circuit board for this. To be honest, it's not worth bothering. It's usually cheaper to buy one of these little breakout boards. But this is where you come into the thing here. So when it starts, the bus master must output the address of the slave it's accessing. Okay, fair enough. I2C stuff is fairly normal. This is fairly standard. There are software libraries that talk to this, which we're going to use. But this is where you give it the address, you tell it whether you want to read to it or write to it. That's fine. We'll have a look at the code on how that all deals with that in a minute. Now this is where it starts to get a bit more interesting. Right. This thing uses registers. It supports 255 of them. 70 to 249 are listed as reserved. We'll come down to this. So here we are. So register 0 is the mode 1 register. Register 1 is the mode 2 register. There are some address registers in here. There is a thing that allows you to modify all LEDs. I've not bothered implementing any of that. And then the key bit. Each LED, so LED 0, so this is channel 0, has 4 registers, 4 bytes, so 32 bits of information, and that controls that LED, or in this case servo. Then channel 2, channel 3, channel 4, and all this, all the way up to channel, see how this is numbered, all the way up to channel 15. Then as I say, we have reserved for future use. Then we have a few more down here. These ones here allow you to send information to all of the LEDs. So if you want the whole lot to do something in one go, you can use these channels here. It's easy. We then have a pre-scale, which is used to set the frequency. So to set this up, what we need to do is configure, scroll back up here, these 2 mode registers and these bits down here. And we'll have a look at how we do that in a minute. What we've then got, because I mean this tells you what you need to do. It took a little bit of figuring out how to do this, but it's here. So there's certain conditions. You can only change the frequency when the outputs are stopped, for example. So you have to tell it stop the outputs, set the frequency, and away you go. We have in here, though, this is how this thing works. So we've got two 16-bit values. Now we can only use 12 bits of them. The other bits are used for something else. We'll have a look at that in a moment as well. But you have a start time and a stop time. And the output is on between those. Now our servo only cares about that on time and the off time. Doesn't know about the rest of it. That's where it sees it starts. So what we can do with this is we can use the on time. You could set that to 0. You can have that as a constant and only look at the off time. And that sets the width of your pulse signal, which in turn sets the position of the servo. But you've got 16 channels. So what I've done in this code, and we'll have a look at this in a minute, is I've used this on time differently for each of the 16 channels. So each servo fires up at a separate time. Just a little bit of an offset between them. It's not much. What it does is it manages the current requirement for driving the servos. Just makes it a little bit simpler. So we've done that. And here's showing you a slightly longer version of it. And then you come down further, past lots of examples in this. It's a really good data sheet. And here you are. So if I just scroll that to... Will it let me do it? No, it won't. Never mind. Right. Look at the top 4 rows. This is for channel 0. Everything else is the same. So you start off and basically you've got a 16-bit value. The lower byte, low, is in here. And all 8 bits of that are used for the pulse width modulation. You get the high byte and the lower nibble, the lower 4 bits, stick in front of this, and that gives you a 12-bit value. There is a bit I don't use, which lets you turn them fully on, and then there are some others that you can't use for anything. If you read them, they'll be 0. That nibble is read-only. And then you've got the same for the off time, and here you have another one that says, I want them fully off. Now, if you leave both of those to 0, you're not in either of those modes. And what you then get is the pulse width you want, and that's what we're going to do here. It's less useful here, but if you do actually use these things to drive LEDs, this means you can set up the brightness on all 16 channels. You then have a way to turn them all off, a way to turn them all on without upsetting that information you've put in. But that's basically how it works. Then you get down to, there is something here, the prescale. So I've worked out the values in this here to go with a 50 Hertz bit of code. And there is some code that uses this, and we'll set this. We'll have a look in a minute. The sub-address bits I don't use. All LEDs, this again is where you can set values to everything. Don't use that. Is the active low enable pin. I think you can tell it don't use that. Yeah, I can use a synchronization switch. Requiring an external clock reference. I've never done that. Tells you what state it's in to start with, and you've got a software reset function. And that's basically it. So, I took that and I started writing some code. So if we start looking at the code, got this here, let's shrink this bit down at the bottom. Now, there are 2 libraries. The first is PCA 9685 Servo Controller. And this works. This will work on its own. If we go into a Leopard Street board, I shall find where it loads this. Forget all of that. That's my. Here we are. So this is how you include it. Include that, and to use these libraries, this is all going to be on the GitHub. There'll be a link in the description. You either put them inside a folder. If I open this, you will be able to see this is how this works. So here is my libraries folder, and they live in a folder for the libraries. Or you can put the files in with your Arduino sketch. Excuse me. In which case you'll be able to edit them from within here. I don't tend to do it. I prefer to use a different editor for the library bits, hence why they're in here. Now, the Servo controller library is the simpler of the two, and we're going to look at this one first because you have to set this up first. This is the bit that talks to the hardware. So in here, this is the interface. This is the header file. This tells you anything under public is a function you as the end user can use. You don't need to do many of these. We'll look at how we actually use this in a minute. But first off, we have what's called a constructor. If you're not used to C code, my apologies, this may not make a huge amount of sense, but the constructor is what you call when you say, I want to construct an instance of this object class. This is the class of an object here. This is what it's called. Constructor by default has the same name as the class. It never returns a value. For example, you will use this here. So what I'm doing here is that is saying call this constructor. This is what I want to call it, and this is how it knows it's calling the constructor. And the address in hexadecimal is 40, which is the default address of these boards. It goes up from there, but if you want a different address, you put the different address in there, and that's what that does. And we'll look at what all these functions do in a minute, but literally all that does is take the address you give it and saves it down here in this private. If you're using these libraries, if you use libraries I write, things with the underscore at the front tends to be a private variable. What that means is the user's code can't see that. And this is where you put things you don't want to be changed or messed with. So the only way you can set that address at the moment is when you construct the thing. Begin is an initialization routine. You call that after you've finished constructing it. You call the begin routine when you're ready to. So again, if we have a little look in the code, we're not calling begin up here because this isn't in code as such. This is the global things that are going to happen before we start doing anything. Servo enable pin on here. Remember what I said, the ignore the note, hardware needs updating. This dry throat. This is what connects to that output enable pin. This has got a 10k pull-up resistor attached to it, as I've shown in the little diagram, but this is just simply so the code knows how to do that. The servo controller has no comprehension of that. It probably could, and maybe it should, in which case you would just tell this is where you're going to go, and then at the end of your begin you'd have an enable and a disable function. All it does is write out a digital value to a pin, so I didn't bother. Then we have write register. So all those little registers we just saw. Reg is the address you want to write to, so you want to write to the mode 1 register, which is 0. You put a 0 in there. Then what value do you want to give it? It's fairly straightforward. Read register, in reverse, you tell it what register you want, and it will give you back the value. uint8t is an 8-bit unsigned integer, which is basically 00000000 in binary, or any of those as ones. It's basically a value between 0 and 255. Set frequency. You give it the frequency you want in hertz. So set frequency bracket 50 sets it to 50 hertz. The way I've coded this, you don't need to call that. By default, the begin function uses a lot of these. So then we've got set position. Now this is where you start to get into actually controlling the servo. So you go in here, channel. Channel is 0 to 15. And int8t, this is a signed integer. it works between minus 90 to plus 90, so you've got 180 degrees of movement. The servos don't actually move 180 degrees. It depends a lot on the actual servo, and there's a little bit of calibration you need to do. This library doesn't know anything about this or care. But that is, say, I want to set this servo to its midpoint. You would go channel 0, angle 0, and the servo will go, and it will go straight there. Set PWM actually does exactly the same thing, except its value that it takes is between 0 and 4095. However, you need to know what the individual servo will accept if you're going to do that. And spoiler, we'll just have a quick glance in here. It will accept between 104 and 508. We'll come back to that. So here you can set an angle, and it's only in whole numbers. So you can go, I want to go to 0, I want to go to 1, I want to go to 2. If you want to go to 1.5 for some reason, you need to start playing with this one, and it gets a bit more complicated. Essentially, set position works out the pulse width modulation value and calls this second function. This one came first. Map. Now this one's actually a bit of a legacy. It's almost not needed. With the Arduino library, map is a standard function. I was writing this for the Raspberry Pi, which doesn't have this. Now what this does, this is quite clever. Long means it's 32-bit value. There's also uint 32t will do the same thing, but this is just how it was set out for the code I blatantly copied this from, so that's where it came from. So you take a value here, and you're going to give it an input range. So here I'm going to say 0 is my input value, and it is between minus 90 and plus 90. And then over here you got 0 and say 4095, and what that'll do is that will say, oh, that needs to be halfway, so you'll get 247. We'll come back, and it just basically says you've got two ranges. The value is in this range, I want the value in that range in the same point. So if it's halfway, it'll be halfway. If it's at one end, it'll be at the same end here. And that's the interface. The code that drives that is here. So as I say, that constructor, literally all it does is store the address. Doesn't do anything else. Later on you call begin. So if we just have a little look in the code for where we call that, forget all this other stuff with the servos, we'll come to that in a minute. OTA setup, we'll keep coming down here. It's the LED driver, PCF. So here we go. So we set that digital write servo pin to high. Now bear in mind it is already pulled high by the 10k resistor. You'll see it's pulled high in a few different places in here. I was having some problems with the behaviour of these servos. I've got one of my controllers has actually got an LED set up so I can see what this is doing. But there we are, we call the begin function. And you have to do that before you call anything else. And what that does, that sets up the mode 1 register, which is that, and it sets up the mode 2 register, which is that, to be what I want them to be. And it sets the frequency to 60 Hz, and then it goes through all, or it used to go through all of the servos and say, sit in the middle to start with. Please sit in the middle. Now what I found was, this was why when I turned all my boards on, all the servos jumped to the center point and then moved to where I wanted them to be. Not really what I wanted to happen. I have got some code a little bit further on that will set where they're going to sit as their start value, so I disabled that. But if you're not using the other servo functions, this is basically how you tell them all to sit. 0. So write register. So this is how, if you've ever used any of the I2C stuff, this is how you use it. Some libraries for some I2C devices are literally, a wrapper that says send this value to it and read it back. You can do it quite easily. This is So begin transmission, specify the address. This tells the I2C bus controller I want to send a message to somebody. So begin transmission, or rather it tells me I want to talk to somebody. So that goes out. And it says right, wire, write. So here we write the register and then we write the value. This depends very much on the device you're talking to, but for the PCA 9685, that's what it wants you to do. It says you write it 2 bytes. One is the register, one is the value you want, and then you tell it end. And it doesn't actually do anything until you say end. And that will write a register byte. So as we look up here, write register, the address, it's the information sent to it. I've done it in binary, basically so you can see what the bits are. If we jump back to the data sheet, and I find the bit for these mode registers. Where are we? That's mode 2, we want mode 1. So what we've got in here, excuse me, we are setting bit 7 and bit 5. So come into here, bit 7, restart. So I'm telling it I want the restart bit to be enabled, and I want auto increment to be enabled. Now auto increment is clever. This is where, and we use this later. Excuse me, our throat's a bit dry. This is where we come into here and I say, right, I'm going to write to that address. So I set the address and I send the data. I can now just send the data, come down and it'll go. So I started at 6, the next bit will go into the next byte rather will go into 7, then into 8, then into 9. Brilliant. So that's a useful function. So we do that. I'm setting up the mode 2 register with bit 012, so let's see what that does. It's been a while since I wrote this. So let's scroll up here. I love these data sheets. I did decide I wasn't going to print this just because of the size of it. So out here, yeah, outputs change on acknowledge. So this is saying when I've written the values, I have an acknowledgement function. Now the reason for doing that is because I'm going to send 4 bytes worth of data in one go, and I don't want it interpreting them until I've sent all 4. So that's what we have with that. So that's write register, read register, very similar, except you send it the register you want, end the transmission, and you now come out request from. I'm going to read 1 byte of data from that, and it comes back and it just sets the function back. Setting the frequency. So here's just various little bits of maths set up. This is set to work basically around 50 Hertz. I've only set this up to work on 50 Hertz because that's all I needed to. So this works out the various other little values. Actually, no, it is set on a bit further than this. This works out the value it needs to be. So I'm going to read in the value of the mode 1 register. I'm then going to change it, do a few other little bits and pieces, and I can write back out. And I'm sending it the reboot command there. We wait a little bit, and that tells the chip to restart itself. Here is the code that says what we're going to position. This is commented, so yeah, this may help people read it a little bit. Here we've got the minimum and the maximum points. These vary by servo. You may find with some servos, if you play around with these values, instead of moving to a set point, it just sits there and spins round and round and round and round and round, which probably isn't what you want. So you play around with that, and this uses the map function. Channel offset. So channel 0, there's no offset. Channel 1, there's an offset of 10. Channel 2, there's an offset of 20. As you can see, it goes through there, and it just adds this puts that little start offset in, and then here this works out 5 bytes worth of information. Now the first byte is the address of the servo, So there we go, and we've told it what channel we want it to use, so it uses that, and it does a little bit of maths on that. It then sets up the other registers. Channel on, channel off are up here. This little operation here says channel on, I only want the lower 8 bits. It's a logical AND operation. I'll do another video on the logical Boolean operator stuff, but that's basically saying I only want the lower 8 bits. The second one, I want the upper 8 bits, but then we're going to shift them to the right. So they will now be... What this is doing is saying I want this one to be the lower, and I want this to be these values, but in those positions. And we carry through, and it writes it out. And when it closes it, that does the acknowledgement. So instead of it taking account of that, and then that, and then that, it just waits to the end. This is the same, except it just assumes you know what you're doing. I thought these routines called each other. They obviously don't. And then this is how that map function works. And that is the servo controller library. It is very simple, but it works. Now we come to the beast, sort of. This is the servo library. Now this does a little bit more. I could have put all this functionality into the servo controller, but what I decided I wanted to do was have things that talked to it. So here I've got servo. This is set up to be a point. At some point I'm going to inherit from this class another C++ concept. Don't necessarily worry about it, but I'm going to call it PCA9685 underscore servo underscore signal. And it will change a few things about how this works. But what it means is the code that's driving it and driving the layout can still say throw, close, which is how it's set up at the moment. Now my software currently on the layout takes the throw and the close command and says, you need to do such and such with a servo, or you need to do such and such with an LED. Well, here it'll just do it to the servo. So starting from the top, we have 3 modes it can live in. Fast is basically, if you can use mode fast, you may as well use the servo controller in many ways. This is, I want the servo to move as quickly as it can. So instead of trying to do anything clever with slow movement, it will just go straight there. Zip, straight away. T constant, this is a time constant, so you can set up, and there are values that control this, we'll come to these in a minute. How long do I want this operation to take? Now, by default it's set to be a second. So when on the layout I change a point, it takes it a second to go from one position to the other. If it's at its halfway point, it takes it a second to go from there to somewhere else. Between any 2 positions, it will take a second. S constant is a speed constant. This is angular velocity, so this will do so many degrees per second of movement. So here, if you go 90 degrees, it might take a second. If you go 180 degrees, it would take 2 seconds. Just different ways of doing things. When I was creating the library, I didn't know exactly how I was going to use this. So here we have a constructor again for the servo. Now this takes a reference. This is a pointer. Again, if you don't understand indirection and pointers, just go with it. Pointers are fun in yeah. It's that one of the hardest bits in C to get hold of. But what we're going to do here is we're going to call this. So I want to say I want to create a servo ampersand servo controller. So that is passing it a reference to that, and this is going to be servo number 0, number 1. I've put them in an array in the actual code. The library doesn't care. You could code them individually. And it says, yeah, here we have, what's the controller, what channel is it? And over here, you have pulse width modulation minimum and maximum, and that can vary by servo. Because I've specified the values here, these are defaults, so you don't need to. But if you know your servos do something different, you can. Or if you're using a lot of servers and they all do something different in the same way, you can just change the values here and they'll all work the same way. Set position, give it between -90 +90, and that tells the servo where you want it to go. If it's in fast mode, it'll go there straight away. If it's not in, well, yeah, we'll come to that. It'll move quickly. Get position is where are we? Set range. Now, this is useful. This allows you to specify some limits. And when I'm configuring, when you've watched me ham-fistedly configuring software, I'm playing with the set range function. Minimum, maximum. You can specify where you want the midpoint to be. The default is it's halfway between the two. But you can specify it to be different. You might always want it to be 0, for example, so you can. Get min, max and mid angle tells you what they're set to. A little bit further down, set them. You can set them individually. You don't have to do the whole range. Get mode tells you which of these 3 modes it's in, and there is a set mode down here which sets it. I tend to do all the ones that return things at the top and all the others at the bottom. Is moving. So if you want to know in your code, is this servo moving? For example, you might want to wait until it finishes before you accept another command. So you've got that. Is thrown. This is something that was added in later. Originally I was going, when I was configuring this, it was like, right, I will get what is my maximum angle using get max, and I will then say set the angle, or set position, and it'll go to that position for me. In the end I came up with, well, is it thrown, yes or no, and down here there is a servo function called throw. So naught is closed, so naught is the normal direction for the point. Throw is the opposite, it's the diverging route. And you just say throw the servo, don't throw the servo. Get address tells you what address you specified to it. You can't change that once it's been set up. Invert mode. Oh, this is a fun one. Sometimes you'll find you've put a servo in, and because of the orientation of the thing, it's backwards. Well, okay, I'll just tell it to go the other way round. Yeah, I just put in a function to invert it, because I want the ability to have throw and unthrow work predictably. You have to configure it. We'll look at that in a minute, but it works. If you need to find out what the constant duration and the constant period are, you can. When I was developing this, I would read those figures back so I could put them out onto a serial port. And down here we're setting all of these values, throw servo, and then loop. Loop is a interesting function. You have to call this in your main program loop, and you tell it how long has elapsed since the last time you called it. We'll come on to why that matters when we have a look at how this works. And then here we've got some function pointers. This is another wonderful little bit of C++. It can be extremely confusing, but what this does, a function pointer is a pointer to a function. Sounds obvious, but what this means is this library is set up so that the end user who's creating the code can say on start move. Now this is called when the servo starts moving. You can say, when the servo starts moving, call this function for me, please, and tell me which servo it is. Okay, yeah, I'll do that. You don't have to. And when the servo's finished moving, tell me that, please, as well. The library code I'm using uses the on stop move to set up the final position of its virtual feedback. And again, we have some private variables down here. These are all the ones we use internally. So by default, we don't invert. The address is 0. It is set up to go from -5 to +5 degrees. That is set because that is a very small amount of movement and it probably won't break anything. Down here, fast duration. So that is 500 milliseconds. This is the software assumes There's always an assumption that it takes half a second for the servo to get from wherever it is to wherever you told it to get to. So you'll tell it to move, the code will tell the servo to move, and 500 milliseconds later it'll assume it has, and it will call this onStopMove function. We are in here, so we have 1000 milliseconds for the time constant. Time constant period is used internally. It's calculated later. And here, yeah, 10 milliseconds for each angle for constant speed. A couple of little flags in the mode. Then we jump into the actual code. This is the sort of scary bit. So again, the constructor, all it does is store the values. And then we're in the loop function. Now this is where most of the work actually happens. So if we're in mode fast, so right, are we moving? Because if we're not moving, we just drop straight out. So when we tell the servo that we want to move, we set that to be true. And then it comes down here and says, well, has enough time elapsed to allow us to move into position? So it has an internal counter, which is, it's just a time counter. When I tell the thing to start moving, it can set that to the current time. Or it sets it to 0. And here it says, well, add in the elapsed time. Every time, add in the elapsed time. And then here we go and says, well, if that's come to more than the 500 milliseconds in total, we must have finished. So we say we're no longer moving, so we're not going to do this anymore. And then if this onStopMove function is defined, call it. And this is a special word. This means it is this servo that has done this thing. So you don't have to know in your code which servo it is. That's relatively straightforward. We now come into the two different constant bits here. So, again, are we moving? We have a constant period, which is, now this is set up when you, we'll look at this when we set the target angle. In the two modes, it actually works in exactly the same way. It just calculates this period differently. And it basically says if the elapsed time is greater than or equal to that period, you can't do equal because you don't know. If you set that to a second, it may not come back at a second. It might be 1.001 seconds. So greater than or equal to. We need to move by 1 degree. So we now need to know whether we're increasing the angle or decreasing it. So we put that through, we map it, and we've calculated the PWM. So we're going to map it against the range we can have acceptably on this servo. Now that's not 0 to 4095. It is between its minimum and its maximum value, which we have set further up. In fact, sets in here. That's what these are. Minimum 104 and maximum whatever that is without scrolling. And it assumes the minimum is minus 90 and the maximum is plus 90. And because it now knows what that value is, it can just use the set PWM function and say this channel, go to that, talking to the controller. So that is going to call this function here, which works out what the actual values it needs to play with are and handles actually writing it. And then again, if we finished, set is moving to 0, which means we stop calculating this loop, then we drop out of it. And that's it. And the code you run will call this loop function for each servo every time it iterates. If the servo doesn't need to move, it won't. If it does need to move, it will. And this handles the slow speed moving. Then we have here set position. Now this again works a little bit differently. So in mode fast, it just tells the whole thing, yep, so we are moving, just move, just go there. So it goes zip. And then on start move, well, we'll call the function to say we've started moving. That was the first one that was implemented. It's very simple and very quick. It doesn't really do anything other than what the other system can do, but it constrains the value you've set to the minimum and maximum angle. So if I've told this thing it can go -5 to +5 degrees and you say go to 20, it will go to 5 degrees. That's as high as it can go. Won't go any higher than that. So this is safer than calling the servo controller directly, because it puts some bounce checking in. Then we're down here. So this is time constant. This is the one we're actually using on Leopard Street. Right, so target angle is the angle. So that is our target. What we're going to do is say how far off. ABS is the absolute. So this is the difference between the two. Between where are we and where are we going. So it's like, yeah, okay, fair enough. But absolute means instead of getting a negative number, it's always going to be a positive number, which is useful. If angle delta equals 0, we don't need to do anything. So if we're at, say, the thrown position, and we tell it to go to the thrown position, it's just going to shrug and, yeah, whatever, I'm already there. Nah. Fair enough. And then otherwise it's going to work out how long between the 1 degree movements, and this is to get you the 1 second move. So it varies. So it knows how many degrees we've got to shift, and it can just do a simple little bit of maths and say, right, well, that means the time constant period is whatever it needs to be to mean we'll go in a second. And again, start moving, call the start moving handler, set the counter to 0 because we're starting. This one's a little bit simpler to do with the angular velocity because we know the time constant period is always going to be this speed constant period, which we set up to be 10 milliseconds. That'll work. And then it does the same thing. Get position just tells you where you are. Set range just sets some of these values. And here it calculates the midpoint. So the midpoint is the difference between the two divided by 2 plus the minimum. So it's always halfway between the two. There's no bounce checking on this. There's nothing to say the minimum angle should be lower than the maximum angle. There's no checking on here. It assumes you know what you're doing. That's probably dangerous, but this is microcontroller code. It was designed to run, well, it's designed to run on the Raspberry Pi 2040, which is actually a remarkably powerful machine. It now runs on the Arduino Nano, or in this case now on the ESP32. Get invert mode, set invert mode. It doesn't actually change anything. It stores the internal value, and then when you tell the point to move, that is when it works around. So the invert only works with the throw servo command. So if you're telling it angles to go to directly, it'll always go to them. But here, this is so you can say I want thrown to be minimum or I want thrown to be maximum. Fairly straightforward. Load more functions that just return bits and pieces. You can set the minimum, so this here does actually play around and do a little bit of bounce checking. What this is doing is saying if you are setting it to be an angle below where we currently are, go to where we currently are. So it can, you can go below. The reason it has to be able to go below is when you're calibrating the thing, if it's at -10 and you want it to go to -11, you need to be able to tell it go elsewhere. And this is set up so that it will, in one command, if you say go to -11, it will go there and it will change its minimum position. Same with mid, same with max. You can set all the other functions as well. And that's the library. So if we just have a little look now on how we use this. So here we have the setup. Now I've created an array. Like I say, you don't have to. But by creating an array, when we come to the loop, if we scroll down here to the loop function, I will show you how that works. So here we are, servo loop. And that's it. So I've got to call the .loop function for each of them. Because they're in an array, I can do it in a loop. If they weren't, I would have to have 16 servos down here. Each one, servo _1 .loop. Away you go. Incidentally, this is how you do the elapsed time bit. So what's the time now? T last is set up initially, or it could just be 0, and it's basically the time but you switch the thing on, and it just calculates how long did this loop iteration take. Some of the functions you're going to do in a loop might vary with how long they take, so you can't set how long it's going to be. But here we are, we set them all up. I'm not including the other two parameters, which if I hover over this, will it tell me? Yeah, I've got the constructor there, so it tells me the minimum, the maximum are set. I don't need to set them. I could, but I'm not going to. I calibrate the servos later for the layout. I'm not trying to pre-do it. Down here, I'm going to set the servo callbacks. So I'm saying my start move handler and stop move handler. There we go. Now, they're not set to anything yet. I'm creating this. This is what's called a prototype. So I'm saying at some point my program is going to define this command. The Arduino IDE doesn't need it. It does a pre-scan, it reads them all, it's quite happy. The code on the Raspberry Pi did need it. Because I hadn't defined that when I'm going to set it, it had gone, don't know what that is. So here it is. This is basically a promise to the computer. This is going to exist somewhere, trust me. Other timing settings which are nothing to do with any of this, but that's basically that bit. We then go in down here and we find how we actually set these up. So here we are. So we go begin. Again, we make sure they're off. We're now going to go through this to number of servos. Now, the number of servos can be up to 16. But it could, well, on one controller it could be up to 16. There could be 32 of them here if I had two controllers. Because if you look at the array at the top, it says what its controller is. Now each controller can only handle 16, so I can have another line under this. Servo controller, so I'm going to call it servo controller 2. And it could be on OX41. And then have another 16 of these here that say servo controller 2. Brilliant. And they can all share the same, well, they can't share the same callbacks. Because I would have to modify, I've just realised I would have to actually modify the servo code. It knows what controller it's on. I'd probably end up modifying the controller to say which controller am I. This is basically so that, because the servo, the pointer to it, it's all going to know 1 to 15. So the second lot would also be 1 to 15, otherwise it's going to go wrong. For the future, yes, if you want to use this thing with more than two servo controllers, there's going to be some modifications needed. But what this does, this thing says, right, for each of the servos, set the start move handler, set the stop mode handler, set the mode. By default, the mode is fast. So set the mode to be time constant. Set the minimum, set the mid, set the max. I could use a set range in there, but this is just the default. Now here I did originally say start in the middle. I now don't, because I want to be able to set that per point. And then set the address. Basically I want it to be 1 to 16, not 0 to 15. So there we go. And that address is worked internally, so it knows about that. And here we have the actual configuration. So servo 1, this board Z is my test board. We will do a video on my test board, somebody asked for that. But it says servo 0 goes between -25 and +25, and it is inverted. So this second value is where it goes when you tell it to close, and this first value is where it goes when you tell it to open or clear. That was a 0, that will be clear, that will be thrown. And there's a second servo set up as well. This board, I believe, if we come up to here, number of servos 8. I have actually told it to do more servos on this, but I haven't set them up here. So what this means is servo 2, 3, 4, 5, 6 and 7 are all going to use these default values, so they won't move very much. But they will center because its default midpoint is 0. So if it's not told what to do, this, when I did this set position, this is saying set the servo to position 0. If I don't set that to anything, that individual servo is not set and it won't move, which is quite useful. Then there's a whole load of other bits and pieces here which are to do with the other bits, and then we come down here into, say, the servo loop. That's mostly it. However, this is how we actually control them. So this is the MQTT code. So this is a long-winded way of saying if the message is a turnout, get the turnout number, then we come down here and we say servo set servo number -1. So servo 1 is actually servo 0. C uses 0 as its base for numbering. A lot of other systems, including humans, tend to use a 1. It says, right, throw servo 0, because this is C, so this is closed. And then we come down here, and this is always the same, so this works quite happily. Servos, well, in this case 1 to 8, because that's the highest number. It won't get any more of those. Up here it's capping it at 16. That is to stop, if you say servos square brackets 27, your hardware will probably crash, because that doesn't exist. So we clip that a little bit. There are probably people who can do far better programming tutorials than me, but if you want me to have a go at one, please let me know. So that will throw the servo. Then we come down here and we do some stuff with the relays. We don't care about that. And then here we are, throw servo 1, because it's thrown, so it just does it the other way around. And again, setting up the frog relays. Frog relays are completely separate to the servos. The servos don't know what they're driving. And then here we are, we set it to its set position 1 is the midpoint. Let's just go. What that's actually doing is telling it, I can't tell it to go to the midpoint. I'd have to get the midpoint value. So I told it to go to position 1. This is because originally when I wrote this, if I told it to go to position 0, it would crash. It now doesn't. But we carry on past all of this nonsense, which is controlling lighting. This is all the MQTT connection, Wi-Fi connection, the I/O boards. Now these, it's not there. Right, start move handler. Remember, this is called when a servo starts moving. Now I don't have switches connected to these points as to act as sensors. I have a virtual sensor. So what I do is this bit of code here, but this just demonstrates how you use these handlers. So if, say, servo 0 has been told to move, it'll call this with a pointer to servo 0. So I go servo get address, that'll be 1, because servo 0 has been told you are number 1. And this will create a message that says track sensor board ID, so this would be Z, so this would be ZT, gets the address 1 thrown, and it'll say inactive. And you think, see, that clears things. And it'll set the closed version also to inactive. The reason it does that is because when the servo is moving, it is in neither position. Then there's a separate feedback channel I use that says inconsistent. This is so you can have, if you think you could put an LED on both of these channels, which would tell you where the point is, and if neither of them are lit, the servo's moving. We could also have an LED that sits in the middle, maybe a yellow one that says, warning, not moving, or a red one, you can't root through the red signal. The screen stuff, forget about that, that's doing something else. And then when it stops, it comes in here and it works out which way round the point is. So is it thrown? This again uses the library function. And if it's thrown, it sets the thrown servo sensor to be active and the other one to be inactive, and vice versa. And then clear the other way around. This using the is thrown bit means that works with the inverted functionality. Just moving a box. And that's basically it. There's a whole load of other stuff in here that isn't needed. Now, I'm going to put this up on the GitHub. I'm also going to put up the, I think that there already is board controller things. I'll put the board Z one up when I actually do board Z. There's a few other boards that are up there that talk to these things. But what this means now is if anybody actually wants to compile a board controller piece of software, you should be able to do it. The only library I've created are these two. Sorry, libraries I've created, it's plural. All the rest are standard libraries. So if you run up to the top of this, This sort of tells you what you need. The Adafruit SSD 1306, this is the little screen I use. Sets that up. The Wi-Fi library is a standard library. PubSub client handles the MQTT. So that's how to. If you're on my internal network, that's how you connect to my MQTT server. This is one of the things I recently have had some fun with, resetting my internet router of all the addresses, trying to change and trying to say no, you're not changing. You're using the same address. But that's that. Yeah, the TLC 5947 controller, that is this is an example of one where I decided instead of writing my own, I was going to use the existing Adafruit library. This is for the LED controller. Again, I'm using a standard library here on the PCF 8575. By the time I came to do all of this, these libraries existed or would compile on the Raspberry Pi. The servo controller, there wasn't a library I could find that did it. So, and then we come down here. So there we are. And that, ladies and gentlemen, is my servo control code. Like I say, this will be on the GitHub. Feel free to download. It is all open source. You can do whatever you like with this. It doesn't come with any warranty. If you find a really glaring bug in here, please let me know, because I've probably got something going wrong somewhere and I'm not noticing it. But there we go. Like I say, at some point in the future, I'm going to modify this to talk to signals. So I can put a little bit of bounce on a signal. You know, you'll get to the end and it'll go one point, then it'll bounce a little, and then it'll settle down. You can do all that sort of stuff. But it'd need to be modified to do it. But the idea is you just tell the signal to move and then forget about it, and it does all that for you. But that is that. So I shall hand it back over to myself, and yeah. Right, so that is a quick look, at the dark art of my servo control library. I'm aware that's probably not to everybody's taste, sort of coding videos. It's a part of what this layout is. Where have I got this light behind me? If I do that, yeah, this layout is, for me, personally, this is as much an electronics project and a microcontroller and a software project as it is a model railway. To some extent, the model railway is an excuse for the electronics to exist, and I like trains, so that's why I picked this as the subject matter. Like I say, that software libraries, they're already on my GitHub. I will put a link in the description. I hope this has potentially helped those of you who are interested in, can you actually do this? You don't have to do it this way. There's lots of other ways of doing it. If all you want is a servo to move slowly, the methodology I've used will work quite happily, and you can just write it directly. You don't need to use these libraries. I did it this way because I wanted to see how to do it this way. This is a fundamental thing with a lot of stuff on this layout. It is more complicated than it needs to be because I was trying to work out how to do it that way. I mean, I could have just used a commercial servo controller. I could have coded the servos to work directly. I could have used what I actually did on Dingleberry, which is keep this little keypad in use and the little memory chip. So I could plug into a board and say, I need to configure these points. I should do that. Save. And then all the computer does is say throw or close, and it's all the board knows. Because I'm going to be updating software, doing it like that on a separate EEPROM chip for each board actually would work quite nicely. But you only have to configure the things once. Once you know the value parameters for either extreme of movement in terms of degrees, that library works. I haven't, but I could say to that library, instead of moving 1 degree at a time, move in microseconds. So if instead of it being 20, 30 degrees difference, it might be 150, 300, 400 steps difference. So instead of it saying, right, I want you to move 30 degrees, it might be, I want you to move 300 steps. And the movement would be a lot finer. I don't need it. So I've got this. Anyway, that's enough waffle. That's enough for this video. If you're still awake, well done. You deserve a medal or a biscuit or a cup of something nice and refreshing. Otherwise, I will see you all in the next one. Likes, comments, shares, etc. more than welcome. Next video is going to be post the weekend. I should have more signaling working. I should have more lighting working. And I'm working on the bits. It's the first part of it. The controller for the M board. That's probably going to take another week or two. We'll find something to do anyway. Meantime, enjoy the rest of your weekend. Thank you very much for watching, and goodbye.